Welcome to the course on advanced power electronics. So we'll cover today induction motor drive as a typically application. So we'll talk about first outline types of induction motor and working, control of induction motor, dynamic modeling, scalar control, vector control, model reference adaptive control, sensorless control, and fault tolerant control. And we'll talk about case study of power quality improvement in induction motor variable frequency drive, then we call converter induction motor drive, and then power quality improvement in multiple converter fed multi-level induction motor, sold example and numerical problems and references. So induction motor can be classified as wound rotor induction motor and squirrel cage induction motors. And typically you can see the photograph that how squirrel cage and wound rotor look like. And coming to wound rotor, in wound rotor induction machine, the rotor circuit is made of three-phase winding, similar to that of stator, and rotor winding are then short circuited by end rings. So because of high cost, the need for maintenance, lack of extended, the wound rotor induction machine is less attractive than the squirrel cage counter, however, especially for electrical electric, and the squirrel cage induction motor is loosely named as induction motor for EV propulsion. However, the wound rotor induction motor in the last couple of decades have been for wind power application, which is very widely known as called doubly fed induction motor with the couple converters on the with lot of power electronics or advanced power electronics on the rotor side, like for wind power generation. So coming to squirrel cage induction motor, in squirrel cage, the rotor bars are inserted into by die casting, where the melted aluminum or copper is molded in the rotor slot, and the bar are then short circuited by using end rings. And this is a typical process how really end rings and brazing paste with rotor bars and the complete manufacturing of fabricated rotor. And this is typically with the manufacturing of die cast rotor bars. So coming to general induction machine are categorized number of stator winding like single phase and three phase induction motor, and typical example of single phase induction motor and the three phase induction motor, and basic concept of induction machine topology, and then typically you can call it the rotating magnetic field, typically with the three phase current excitation. The balanced three phase winding is supplied by three phase supply. So three phase currents are I equal to Im sin omega t, Im B equal to Im sin omega t minus 20, Ic equal to Im omega t minus 240, where Im the peak current and omega is the angular frequency of applied current. And these are the concept of working with the rotating magnetic field by graphical method MF waveform, and the typical resultant MF, F equal to sum of the three, and that becomes typically F equal to 3 by 2 FEM e to power omega t, and the RMS has a constant amplitude of 3 by 2 m and rotates in space. Now coming to develop torque as a working principle, as the rotor windings are short circuited, current flows through the rotor winding, and interaction between rotating flux produced by the air gap by the current in the stator winding and the flux produced by current in the rotor winding produces torque. The electromagnetic torque expressed as T induction K equal to K BRBS, and where T induction is the induced torque and B and BSR are the magnetic flux density of the rotor and the stator respectively. And the electromagnetic torque is in the induction motor is the same direction as that of the rotating magnetic field. So if the rotor is stationary, the induced EMF and current in the rotor are maximum because of the relative velocity between rotating magnetic field in the air gap and the rotor conductor are maximum. If the rotor starts rotating in the same direction of rotating magnetic field, the relative velocity decreases along with the lower value of the induced EMF and current and its frequency. So the term slip is defined in the difference between the synchronous speed and the rotary speed, expressed as a ratio of synchronous speed is termed as slip in induction machine S equal to ns minus nr upon ns, where ns is in r the synchronous speed in revolution per minute, and the rotary speed is expressed as r equal to ns minus 1 minus s. So at standstill s equal to 1, the rotor frequency is same as the supply frequency of stator winding, and at running condition s greater than 0, and for s less than 0 is the rotor slip is times the supply frequency less than 1, and that synchronous speed s equal to 0, the rotor does not rotate. The induction motor have magnetically coupled circuit, the stator and rotor. The latter is short circuited. The induction motor is similar to the transformer, whose secondary is rotating and short circuited, and the motor has balanced three phase circuits. Consequently, the single phase representation is sufficient for analysis purpose, and both the stator and rotor have windings which have resistance and leakage inductance. Coming to equivalent circuit, the stator and rotor windings are represented by resistance R1, R2, and leakage reactance X1 and XR or X2, which are connected in series. The magnetizing reactance with the resistance connected in parallel to represent the magnetic field generation in the stator winding, and the resistance RC represent the eddy current and hysterical losses in the iron core, and the current in the stator poles, that is the which have the constant magnitude and rotate with synchronous speed. And this is the equivalent circuit, virtually you can call it, of the inductor which produces the induced voltage. From stator side, we have a resistance of stator, then leakage reactance, then the shunt branch for representing the core losses as well as magnetizing current. Then we have a typically the transformer action with the which is not only transverse but the slip also comes into on the rotor side. So we can say induced EMF per phase in the winding is nearly equal to the per phase, and given by Vs equal to ES equal to 2.22 kWsF phi ZS, that is 4.4 kWsF phi TS, where all these variables are defined. And the induced voltage in the rotor winding ER equal to 4.1 kWr FR phi RTR, where all these are so induced EMF in the rotor winding with the motor running at a speed proportional to the rotor frequency, assuming the winding factor and both winding are same. So induced EMF is FR equal to SF and ER equal to SES, where the rotor is locked or blocked, so S equal to 1. So large voltage and rotor frequency are induced in the rotor. They rotates at synchronous speed S equal to 0. The induced voltage and frequency in the rotor will be equal to 0. And leakage reactance, so at the frequency of induced voltage in the rotor changes, the reactance of rotor circuit also changes. So XR equal to omega RLR, that is 2 pi FRLR, so that is equal to 2 pi SFLR, that is S into XR0. So XR0 is the rotor reactance and supply frequency under blocked condition, and the rotor current is defined as R equal to ER upon RR plus JXR equal to ES upon RR plus JXR0. So dividing both numerator and denominator by S, so nothing changes, we get it IR equal to ER0 upon RR upon S plus JXR0. So ER0 is the induced voltage, XR0 is the rotor reactance at the block rotor condition, S equal to 1. So the equivalent circuit is that typically ESR, ER equal to S0, and that is JXR, JXR0 and RR. And when you divide by the slip, so JXR and RR upon S, modify equivalent circuit. And then the referring the equivalent circuit on stator side, so you can see here R1 X1 shunt branch across ES, and then X2 and R2 IS, that is referred to the stator side as it is the by turns ratio, it is shown here. So now coming to losses, copper losses in stator is I1 square R into 3 for 3 phase, and copper loss in the rotor is 3 times I2 square R2, and core loss P core, mechanical power loss due to friction windage. So this is the power flow diagram. P equal to 3 VS I1 cos theta, and where we have a stator copper loss, then rotor is then core loss, then the rotor copper loss, then friction windage loss, and then stepper loss. This is initially, and then that gives the output power, which is equivalent to T load into omega m, the torque developed torque, and equivalent to load torque multiplied your rotary speed. So now power relation, input power P equal to 3 root 3 VL IL cos theta equal to 3 VS IS1 cos theta, and stator copper loss is PSL equal to 3 I1 square R1, and air gap is PH equal to P in minus PSL plus Q core, that is P converted plus P RCL, and that is 3 I2 square R2 IS or P RCL upon S, and the rotor copper loss PRCL is 3 I2 square R2, and power at the shaft is P converted PAG minus PRL RCL, that is equal to 3 I2 square R2 1 minus S upon S equal to PRHCL 1 minus S upon S. So output power P out equal to P converted into minus P friction windage plus P stray losses, and induced torque is T or developed torque is T induced equal to P converted omega m, that is 1 minus S in PAG divided by 1 minus omega S. So PAG versus that PRL versus converted is 1 to S in then 1 minus S. So now coming to Thevenin theorem can be used to transform the network into left-hand point of the A and B into equivalent voltage source in series with the equivalent impedance REQ. This, I mean, you can see from the equivalent, this equivalent circuit, maybe from exact equivalent circuit also comes in the similar manner. So from the equivalent circuit we can say 1 EQ equal to V1 ZM. In place ZXM we can put even the parallel circuit of RM, RC and JXM divided by R1 plus JXM, that is REQ plus JSQ equal to R1 plus JX1 in parallel to JXM or ZM, and R2 equal to V1Q upon ZT, that is V1Q upon under root REQ square plus R2S square plus XEQ plus X2 square, and the internal mechanical torque is X plus T converted to P converter upon omega, and P converter 1 minus S into omega I2 square R2 by S upon omega, and this T converter become 1 upon omega S in V1 EQ divided by under root REQ plus R2S square plus SEQ plus X2 square into power square into R2 by S. So coming to maximum torque occurs when the power transfer to R2S is maximum, and this condition occurs when R2S equal to the magnitude of impedance Req plus jXeq plus X2, and that R2 Tmax be equal to R2 Req square plus Xeq plus X2 square, and Stmax is R2 1 under root Req square plus Xeq plus X2 square. That is the torque is characteristic for motoring as well as generating rates. Virtually we normally operate with variable frequency side only in stable region from your typically in the slope where motoring and generating both are utilized. For generating we use the regenerative wing, motoring side we use for typically for motor control, and this is typically with the torque speed characteristic typically of a squirrel cage induction motor. And defining different terms like lockout torque, pull out, and then the breakdown torque as well as full load torque. And then the torque is characteristic relation for small ships is approximately straight line. I mean, which is virtually we use for with the variable frequency drive for line AB in the range. Now coming to this characteristic, if the motor is unloaded, it needs very little torque to keep running, only enough to overcome friction and impact. So as an unloaded motor will run with a very small slip at just below the synchronous speed as shown in figure. And when the load is increased, the rotor slow down and the slip increases, thereby inducing the more rotor EMF and current, and thus the more torque. The speed settles when the slip has increased to the point where the developed torque equal to load torque, for example B in the figure. So if the slip increases, the rotor will do more mechanical work than increases the stator current. So since the extra current is associated with the supply of real mechanical output versus power as distinct from original magnetic current, which is reactive, and this additional work component of current is more or less but in phase with the supply voltage as shown in the phase diagram. I mean, typically you can see stator current versus the curve depending upon on the no load, part load, and full load. How the current increases, magnetic current remain constant, the load current component increases, and this is the typically the stator current. And your torque, I mean, percentage, of course you can say the current varies from during stable region it varies from up to 100%, but unstable region of course it goes to like a 600 times as you can see here. And maximum torque is normally depending upon the design, it goes from 3 per unit to 6 per unit. And this is the how the effect of rotor resistance on the typically on the torque characteristic. As you increase the rotor resistance, your stable region extended to, and it can be even such large that the whole of the start, I mean the even the starting to this, it can be in the stable region. That's the one of the method of starting control, because by increasing the rotor resistance reduces the starting current as well as increases the starting torque, and that is the method we use for wound rotor induction motor. So in real application where kinds of load exist in different curve, constant torque work and variable speed, screw compressors, conveyor feeders, variable torque and variable speed like fan pumps, and constant power load like traction drive, and constant power and constant torque like coiler drive, and high starting breakaway torque followed by constant torque like shredder and screw pumps. And these are different kind of the typically torque characteristic for all three cases what we discussed, and typically constant power load as well as the constant torque power load for electric vehicle especially. Coming to control of induction motor, so necessary for induction motor to enhance the overall performance of the induction motor. Considering the squirrel cage induction motor is the most robust and cheapest motor today in the world, and that we have to control with the variable frequency source. So that's the reason you prefer that. To provide the wide speed net, to improve the efficiency in all speed, to assure the stability and safety operation of motor, to improve the reliability of electric propulsion system, especially for some applications, to increase the efficiency in regenerative braking. So coming to dynamic modeling of induction motor, so various induction motor voltage equations are derived in synchronous reference frame as well as in stationary reference frame. The coordinate transformers are heavily involved in the process of deriving the induction motor dynamic model, and derivation process is somewhat complicated if the rotary speed is different from synchronous speed. And dynamic model is in synchronous reference frame provide the basic for filtered rate control, and time derivative of the flux linkage yields a voltage equation. So first the stator and rotor flux linkage equations are described in stationary reference frame, then mapped into synchronous frame. So coming to flux linkage, the stator flux is excited by both stator and rotor current. So stator flux linkage is lambda ABS in stationary frame, L ABS into IBS plus M theta R ABS R. So where lambda ABS is the stator flux linkage, LBS is the stator coil inductance, MR is the mutual inductance between the stator and rotor coil, and IBS is the stator coil current, ABCR is the rotor coil current. And this is the typically in uniform air gap fill, the stator flux generated by typically LABS into IABS. So you can see how the inductance matrix and the three-phase current. LS is the leakage reactance, LMS is the mutual inductance between different phases of piston coil. And these are typically the contribution of A phase flux by the B phase hysteresis current and by the A phase hysteresis current. Then you can call it the term corresponding to M theta R IABR. So that is typically inductance metric function of theta R, that is rotor angle, and the three phase current, and the rotor flux linkage lambda ABR equal to LABR IBR plus M theta R IBS as rotor frame. So lambda ABR is the three phase flux of the rotor and coil. So LBR is the rotor inductance, and from the rotor frame the hysteresis current looks behind the angle theta R, thus minus appear in M. So the rotor flux generated by the rotor current is equal to LABR into IABR. So these are typically inductance metric multiplied the current. We are considering the rotor as a air gap as a smooth. The L are the locality and LM is the mutual inductance. And they typically you can call it the two-phase transformation can be applied for both flux, linkage, and current. The same transformation, to convert from your any variable to dq. The theta is the speed of the variables. Either rotor or stator, you want to convert into typically for the reference frame of dq. So you can call it lambda dq is the lambda ds squares. So lambda dq is lambda ds plus 2 component of qs, and lambda ds is 2 by 3 of lambda as plus e to power 2 by 3 lambda bs plus e to power lambda cs. And in stator flux in dq stationary reference frame lambda is ls idqs plus lm I to power didr, LLS 3 by 2 LMS plus leakage, LLS or LM equal to 3 by 2 by 3 LMS. So rotor flux in dq stationary frame with reference to rotor. So lambda dq rotor reference frame LR into IDR plus LM minus IDR into IDR, where LR equal to 3 by 2 LMR plus leakage, LLR plus LM equal to 3 by 2 LMR. And these are typically volt ampere equation in dq reference stationary reference frame with VQ, and the rotor voltage normally in cascade motor is short circuited. And these are typically you can call it the impedance matrix multiplied the current in stationary reference frame. So in stationary reference frame, when you transform the rotor quantity comes to zero speed, that's why the minus omega r speed is involved in this model. So the second is short circuited is skull cage rotor. So VDR VCR is considered 0. P is the differential operator, omega r is the speed. And then you can just see how typically you can convert to typically stationary frame to synchronous rotating frame. There of course your theta is the electrical linkage corresponding to your frequency of excitation of hysteresis, and the flux linkage in dq is lambda dqs in electrical reference frame, ls ids elm e for electrical rotor speed, and dqr is similarly idr and dω. So where volt amplification with du are resistance of idq plus p lambda dq and plus j r. So even the stator, all these quantity are bringing to your electrical frequency omega e. That's why this speed voltage appears, and the from rotor comes from rotor speed to, so that's a slip speed omega e mr comes into rotor equation. And typically this in dq reference frame it comes with dsvq is equal to 0, and here you will just find typically the speed voltage for the rotor and stator appears there, and then the slip speed for the rotor, and your current also in the synchronous reference frame. And you can say advantage here that it eliminates the complete matrix from the angle typically theta. And since the rotor side power is 0, the power calculated P equal to P ABCT is 3 by 2 VDS IPS, and developed torque T equal to 3 by 2 P by 2 LM IQS into IDR minus IDS equal to IQR. And this TQR 3 by 2, how did it derive? That comes from typically even by measuring part of LM flux, and only final come T equal to 3 by 2 P by 2 LM upon LR lambda DR IQS minus lambda IDS. Now coming to control of drive. Now for control of the drive, normally we consider the best control as a variable frequency control with a voltage source inverter. So we have a DC source like battery in electric vehicle or many applications. So we sense the current, we sense the position, and then we have a controller command give the switching for inverter. That's the basic configuration of control. We have a typically the control of different kind. We have a scalar control of the induction motor, vector control, which also known as field control and direct torque control. Now coming to scalar control of induction motor type. So it's called variable frequency, variable voltage, variable frequency control, constant V by F control for frequency below the rated. and variable frequency control with constant rated voltage for frequency beyond the rated frequency. For very low frequency, voltage boosting is applied to compensate for the difference between the applied voltage and induced EMF. This is a typically block diagram of variable frequency variable drive. So you have a reference speed, you have a feedback speed, then you have again, then you really calculate from motor speed the voltage and frequency applied for inverter and next motor drive, where external torque is applied, and this is the typically how the boosting, initial voltage boosting required for, because there is a difference in constant VYF and constant flux mode. To take a full capability, we prefer to use constant torque operation. So the outer loop is speed loop, then we have a PI controller to give the reference torque, put the limiter with the, we get the slip frequency multiplied the speed B by 2, so we get the synchronous speed, and once we have synchronous speed, that's the frequency, and by V by F table we get the voltage applied. So we give the this to control the, as it is shown above diagram, to inverter control, and this is the typically complete torque speed, how really the motor control is there. So normally we control only in stable region. I mean, this entire motor for generating, motoring, for coordinate operation, forward reversal, regeneration, as well as forward motoring, reverse motoring in the zone. So up to base speed we maintain constant flux, and above than that we of course cannot, because voltage cannot exceed, only frequency have increased, so that cause the field weakening automatically. So this variable voltage, variable frequency control, the induction motor drive characteristic can be divided in 3 operating region: constant torque region, constant power region, and high speed region. Limitation air gap, flux drifting, sluggish response, and less attractive for high performance. Typically induction motor drive for electric vehicle like Tesla is using. And this is a variable voltage, variable frequency control. As you can see, the different variable, how the current is maintained. I mean, like how the power, slip, and torque, and then the power with the speed are maintained. Operating capability of this variable frequency control drive. Now coming to full loaded control of induction motor drive. The full loaded control offers the vector control refers to all machine control method that split the current vector into the flux and torque component and control each of them independently. So the phase currents are transformed into synchronous reference whose d-axis is aligned with the vector, flux vector, and the d-axis current determine the flux magnitude, where the q-axis current being orthogonal to the d-axis control the torque. And in case of induction motor, depends on the flux on which the frame is referenced, the control methods are sorted out. Typically rotor flux center control, straight flux center, air gap flux center control. Among them, the rotor flux center control is the most popular for simplicity and good decoupling. And stator flux control gives the coupling effect which needs to be compensated by the decoupling compensation current. So based on the flux angle axis method, the field controls are categorized as direct and indirect methods, and direct field control relies on the flux estimate or the measurement, and the flux can be measured by using flux sensing coils or Hall devices. However, it's not easy to install a sensing device in the air gap or slot, and the signal processing circuit has an extra cost. So sensorless control is a collective term of field control methods that do not utilize the speed or position sensor. It is an attractive choice for electric vehicle. And these are typically that you can call field control implementation, that you have a speed feedback, either you are sensing or you are typically estimating. Then we have a PI controller, and then we have a flux versus speed. So we get the flux, also reference flux. With reference flux and the torque, we go to the like a supply generator with we have a estimation from sense parameter like a speed and flux and torque. So we calculate the torque versus speed estimator, the torque, and then the estimate the flux, and that we use supply, and then supply generator give the typically for inverter and induction motor with the external torque. And these are typically, you can call it field control method, typically where we have a hysteresis current AB and rotary speed through ADC for the processor DSP or so, and then we have a field control, and then we have field signals through optical isolation we give to 3-phase voltage source inverter. And this is typically the diagram what it is done in the control. So we have a reference speed. I mean, typically then we are getting from the feedback speed, and we give the speed control which gives the torque producing component as it comes there, and then we get from this actual speed we get the reference flux, and from which we get the IDS, and from these two IDS IQS we transform into I alpha I beta, with of course there we use the angle of flux angle which is calculated from the slip speed as shown here. slip is calculated from typically from your torque producing component, and from this alpha beta we convert to 3-phase AC current, which are with the hysteresis controller or any current controller with the sense current of stator. We give the PWM signal to the 3-phase inverter driving the motor. So it is favored because the algorithm yields a natural decomposition role of D and Q axis current, and the D axis of reference frame aligned with the rotor flux, that is lambda EQR equal to 0 and lambda E dr equal to the torque equation becomes here in oriented control T equal to 3P by 4 Lm upon Lr lambda R E to IQS E, the roles of IDS and IQS. So this equation is comparable to the torque equation of equivalent to DC motor, and the similarity with the DC motor are lambda dr correspond to the field and IDS E correspond to field current and IQS correspond to armature current of DC motor. So it's controlled similar to the DC motor. So now the roles of current are summarized in the following. IDS is used solely to generate rotor flux. It like say the field current of the DC motor. IDER is the 0 in steady state. Only the Q axis current IQR flows into the rotor in order to nullify as possible generation of the Q axis rotor field current caused by IQE, and IQS is used to generate the torque, and Q axis current is the armature current in the AC motor. So it is the control method of aligning the D axis with the stator flux. It is known to be less sensitive to motor machine parameter and produces more torque than the rotor field current scheme, and the torque flux decoupling is more difficult. So now stator flux and slip equation derived. Slip is PD omega SL in radian per second 1 upon tau r plus P sigma LS IQS divided by lambda P minus sigma LS IDS equal to 1 upon sigma r P plus P IQS divided by lambda divided by sigma LS minus IDS, and the torque equation corresponding T equal to 3 by 4 lambda ds equal to IQS. The torque equation in terms of ID IQ are 3 Tm equal to 3 by 2 P by 2 Lm square Lm plus Lr into ID into IQ. So the flux and slip are not decoupled in the stator field under control. So especially omega L is involved in the field flux calculation. So in term lambda is used for slip calculation. Further, the slip equation contain differential operator P, and thus it requires differentiation of IQS, which is disadvantageous. Now coming to field weakening control. Why the field weakening control? When the speed increases, the back EMF grows. At the rated speed, the source inverter voltage reaches its limit. To operate the machine above the rated, both torque and field have to be reduced. Now these are typically the diagram characteristic in constant field and field region. So you can see how the flux is reduced, how the torque is reduced, and how the current is changed, and typically in different region, and how it is the typically power is changed. So now with the rotor field under control, the torque equation is expressed at T equal to 3 by 2 P by 2 Lm square upon Lr IDS and IQS, and hence the constant torque curve appear as a parabolic curve for the type pi equal to C upon X. So this is the simulated performance for field under control. So you can see initially with the low frequency and frequency increases. So initially the frequency of stator and rotor equal, and then the stator frequency increases. To increase the advantage of this, we operate always in stable form. So here you can see for initially starting, then the load disturbance and reference speed difference increase and decrease. So all are shown here with the dynamically, and you can see there is no inverse current. So current is well limited to, and DC link voltage maintained constant. So these are experimental typically waveform corresponding to that, how the current changes during starting and steady state of stator current and speed, rotor and reference speed, and how the dynamic performance during FLC during field weakening control. As the speed increases, you get the field weakening, and dynamic performance of AC during sudden change in the reference speed. Then the dynamic performance of dipolar and change in low torque. Now coming to another control called direct torque control. So the main features of direct control of flux and torque by selection of optimum inverter switching, and direct control of stator current and voltage, and approximately sinusoidal and stator flux and stator current. Possibility of reduced torque oscillation, and torque oscillation depends upon the duration of zero switching vector and high dynamic performance, and inverter switching frequency depends on the flux and torque stage band. So main advantage of direct torque control is absence of coordinate transformation, absence of separate voltage modulation block, absence of voltage coupling circuit, absence of several controllers, and only your sector position where the flux linkage vector is located has to be treatment with 60 degree. accuracy, and minimum torque response time. Main advantage possible problem during starting and low speed operation and during changes in torque command and requirement of flux and torque estimator and changing switching frequency and high ripple torque. So these are typical block of direct torque control. So we are sensing the current, speed and DC link voltage from which we are estimating the torque and flux in DTC controller, and then we have a reference torque and speed, reference torque and the flux from the controller, and then we control both with the help of optimal switching, and then we give the output signal for inverter control. So this is the diagram of your ABB direct torque control. Here you can see that what we are sensing the typically DC link voltage, and we are sensing two current. So from and the switching, virtually switching position of inverter. So from this we are estimating the typically the actual speed, we are estimating the actual flux in the motor, and then we have a typically a speed controller, so with PID controller, which gives the typically the reference torque, or we can have a torque reference also directly as shown in the block. So we get finally the reference torque, and we have a estimated torque also in torque and flux controller, and similarly we have a energy optimizing on off control or braking control here in the another block, from which we get internal reference flux. I mean, sometimes we enhance the flux during starting as well as control the flux during braking, and from this reference flux and reference torque along with the your actual estimated flux and estimated torque, we go to table and flux control, and from which we get the signal which called optimum pulse generator, or we call table of optimal switching. We give the signal to the inverter. You can see it's essential as control. We need only two current and DC link voltage in this total process. Like, so this is the more detailed block how it is going. So from starter current, DC link voltage and speed, we are estimating the torque and flux, and then we go to from the speed controller, actual speed, we get the flux reference, and we have estimated flux, so we go to the flux two level controller, and we have a from PI controller speed control output, we get a reference torque, and we have estimated torque with go three level torque controller, so we get a stress error between torque and flux, and from which we give to support the switching table. It's all called table of optimal switching, which give the 6 switching signal for 6 devices. And this is the simulated performance of direct torque control. So you can clearly see how the current are really control and how the speed control for starting, then increase in reference speed, and then reduction of speed as well as the low torque chain performances. And this is the typically the performance of typically with the, you can call it your reference speed chain and the load chain. I mean, pump typically 50%, then decrease to from low to 50% or 100% also. And these are experimental results of DTC drive under steady state and rated speed condition, and dynamic performance of drive during field weakening for direct torque control. And this is dynamic performance of the sudden change in the reference speed. So now coming to model reference adaptive control for induction motor. The model reference adaptive control is an adaptive mechanism is adapted which aims to force the motor drive following the reference model even after the variation of system parameter, and ensure the robustness with the asymptotically zero error between the output of the reference model and the motor drive. As a reference model is made to certify the desired dynamics of the motor drive, and the command input, the control motor drive output, and the reference models are required to establish this control scheme. And this is the block of model reference adaptive control. So here also you can clearly see a motor we sense the speed, and then we have a sense current. So from this we calculate typically in the adaptive mechanism we calculate the voltage, and finally from the speed control we get the torque, and we from this also so we go for anti-decoupling control of this motor line. So this motor drive control is constituted by two parts: regular input generated by linear model and adaptation input generated by the adaptive mechanism. So you can see UP equal to UP1 plus UP2. And the regular control input is the motor drive is expressed UP1 equal to KE into E0 plus KUM plus KX XM. So where KU are the constant and UM is the model input, XM is the state vector of the reference model, E0 is the feedback error between the omega R, and omega R is the reference model speed, and omega R is the actual motor speed. And the adaptation input is UP2. The adaptation input to the motor drive is expressed as UP2 equal to delta KE as a function of eta and E0 plus delta KU into function of eta and T UM plus K delta KX eta T XM, and delta KE, delta KU and delta KX are the adaptive gain. So eta is the state error vector, and to get the asymptotically zero value of eta PI adoption law can be adopted, and the PI adoption law is delta K equal to 0, your 0 to T M1 V as a function of R1 E, typically T dt d tau plus M2 V R2 E T, and similarly delta Ku as a 0 to T as a N1 V S1 UM T and dt plus N2 V S2 UM, and delta Kx equal to 0 to T L1 V function of Q1 XM T dt plus L2 V Q2 XM T. So where V the compressed error feedback of M1 M2 N1 N2 L1 L2 and R1 R2 S1 S2 Q1 Q2 are the positive constant. And coming to sensorless vector control, so in sensorless field-oriented control is the collective term of field-oriented control methods, and they do not utilize the speed or position sensor. So it eliminates many problems in sensorless installation, sensor installation, cabling, processing, and low signal to noise ratio. Typically in solar water pumping, where the mode is in speed down, or even many other applications also. And this is how the typical structure of sensorless direct torque control. So we sense the current as well as we sense the DC voltage, and we have a estimation of torque, speed, and flux, and then we have a speed controller, flux controller, and we have a switching table for inverter light. Coming to typically the methods, the open loop speed estimators using monitor stereo voltage and current improved scheme, and estimator using spectral saturation third harmonic voltage, and estimators use silency, geometrical saturation effect, and model reference adaptive control system. Adaptive system. So general observers we use for this speed, like for this purpose, general observer observe and extend Kalman filter. And this typically rotary speed as using a 2 indicator, 2 differentiator, and 5. Typically in open industry, you modify stereo voltage and current improved scheme. How the speed is estimated from your voltage and currents. With of course use the parameters. Similarly, typically estimate using a monitor stereo voltage and current improved scheme. The 2 indicator, 1 depend. So different method of speed estimation using the slip speed of the stator flux linkage and space vector, and similarly estimation of rotation by using the speed of the stator flux space vector, and then like MRS based speed estimator, and where again the voltage and currents are used for estimation purpose, and we get the different parameters estimation from this. And then this MRS based speed estimator from using those all blocks here with the voltage and current. Of course, these are DQ currents in state reference frame which are taken, voltage and currents are taken from state side. And this is the adaptive speed observer to estimate the typically how we estimating the speed from the voltage and the current term. And then the structure extended Kalman filter which is used again to estimate the speed, flux, and torque. Now coming to fault tolerant control. For the fault tolerant control, continuity of operation is very important in high impact automotive application. So drive system must have a high reliability and robustness for various vehicle operating conditions, and it also ensures the proper operation of machine under faulty environment. And the concept of a fault tolerant drive system is that it continues to operate in a satisfactory manner for after sustaining a fault. And of course, for fault condition, variable speed drive is typically with the electrical machine cell. Mechanical fault may be a brush wear, shaft alignment, unbalanced eccentric rotor bearing and resolver. Similarly, electrical fault may be rotor fault, broken bars, stator fault, insulation, registration, short circuit winding, and sensor faults may be mechanical variables or electrical variables like current, speed, shaft displacement sensor, or current and voltage sensor. And actuator means it can be power conductor failure or power supply fault. So now coming to fault tolerant control. In induction motor fault tolerance, usually two approaches are followed. First one is active fault tolerant control, typically consists of design with robust control scheme and retaining same control strategy even under fault condition. And two is a passive fault tolerant control, so design with the many control strategy based upon the type of fault, the most suitable control strategy adopted. Now coming to active fault tolerant control, the unique robust controller is adopted with conventional control technique, and it makes the system fault resilient to limit the failure sets. It ensures the continuity operation only for the predefined faults. At the time of designing itself, the controller is designed in a robust manner, and it includes the fault diagnosis and isolation block and reconfiguration block. So this is active fault tolerant, that you have a reference, then you have a reconfiguration controller, and then of course in the process we may have a fault either in actuator or process or sensors, and then we have a typically feedback corresponding to the fault detection, diagnosis, and then reconfiguration, and of course we get the typically the feedback in that case. So now coming to fault detection and isolation. The focus of this section is on the isolation of faulty sensor, faulty part, and many algebraic differential observability techniques are used to detect the fault case. And this is fault detection isolation. So with the start, then with the sensor measurement, then compute current credential and check with that threshold. If no, go back, and if yes, then check again with whether it is now your let's say again to check. If no, then flag. If yes, then go to see whether f alpha and beta is greater than 0. If yes, flag C. If otherwise no, then flag B. The flowchart of decision making logic for the right algebraic approach. Now coming to reconfiguration philosophy. Reconfiguration technique are configured by adopting estimation and the sensorless technique. And sensorless technique operates poorly at the very low speed conditions, so it is not preferred in normal operating conditions. So sensorless technique highly sensitive to parameter variation, and these are typically active control of with the inductor motor voltage source converter, and we are just sensing voltage and current and estimating the typically a different variable for fault diagnosis, and then reconfiguration and goes for the use in the control control, and with the power transformation and slip frequency calculation with the vector control how it is really fault and control is also included in this. So now coming to passive fault control, so it's implemented with more than one control technique. So based upon the type of fault, available sensor inputs control transition take place. So this is a passive control. So we have a reference signal, then we have passive fault and control, and then we have a fault in the actuator or system or the sensors and give a feedback for. And these are typically fault tolerant control algorithm for changing the method. So you can just see we are sensing the voltage, current, and speed and giving this control stage decision, and then we go for typically for fault and controller operating in different modes like indirect vector control or sensorless vector control or sensorless scalar control or open loop control according to the fault, and then we convert of course 3 to 2 phase for receiving the supply to the motor. And this is a fault tolerant control algorithm for changing conditions. So here fault tolerant controller is also included in this control along with the sensorless fuzzy control, extended encoder based slide remote control, and fuzzy logic crossover block. Now coming to solved problem, numerical problem. So example 1 is a 3-phase 7.5 kW for 15 volt star connector 4-pole square cage induction motor. For running the electric vehicle has the following parameters: RS equal to 1, RR equal to 0.77, XLR equal to XLS to 1.5, XM equal to 35, J equal to 0.1384 kg meter square, is full load power factor 0.8, efficiency 0.8, full load speed is 1410 rpm, and then speed of the motor is controlled by indirect vector control scheme through field of VSI. Calculate the reference DQ component of stator current and stator frequency at starting. If starting torque is required to double the rated torque. So coming to solution, now rated torque T rated, P rated upon omega rated, that's given the power. So we get 49.22, and starting torque is twice of this, so it comes 98.5, and the slip is your NS upon NR upon NS. So slip we get here typically 0.606% for given speed of 1410 rpm. So the slip at twice the torque will be 2 into 90, 180 rpm, and synchronous speed NR plus slip speed, that is 0 plus at starting 180, that is a 180 rpm, and synchronous frequency for this is this particular slip frequency is for to this, that comes 6 Hz. Now coming to the ratio of operating frequency at rated is 6 upon 50.12, and equivalent impedance can be calculated from equivalent circuit for this particular frequency. So our total impedance comes typically 21.89 at 39.1 minus 31 degree, and rated stator current V rated upon rated we calculate 10.95 at the angle 39.1. Then the IM rated, that is IS rated, and the ISRS upon XL plus LSR, that comes 10. Putting the value this IM rated comes 6.31 at the angle minus 91.43. So ID peak value is ID equal to root 2 IM, so it comes like an 8.92 ampere. And expression for Lacoste dot T equal to 3 by 2 P by 2 LM square LM plus LR do IDIQ. So from here the LM we get XM by 2 pi, that comes 0.114 Henry, and LR is XLR upon 2 pi f. Putting values comes 4.7767 10 to 1 minus 3 Henry, and putting in the torque expression we get IQ equal to 34.44, and MS value is stator current under root ID square plus I square by 2 on root of 12, that comes 25.16 ampere. And the motor power factor angle pi equal to 10 inverse ID upon IQ plus 10 inverse XL IQ upon XL. So it comes typically your pi comes 32.13 degree, and motor power factor is now cos pi, that's a 0.8468, and the hysteresis current is IS equal to 25.16 at the angle minus 32.13 ampere, and rotor current can be calculated IR equal to IS minus IF. So putting value comes 22.60 at the angle minus 18.24 ampere. And since the operation is below base speed, then the flux is rated. So I am rated at 36.31 at the angle 94. So IS is your 25.16 at the angle minus 32.13 ampere. Now coming to example 2, a 3.7.5 kilowatt for 15 volt line 50 Hz star connected 4-pole square cage induction motor for running the electric motor vehicle has the following parameters: RS equal to 1 ohm, RR equal to 0.77, and XLR equal to XLR 1.5, XM 35, J equal to 0.131, is full power factor 0.85, full load power factor 0.5, efficiency is 0.88, full load speed is 1410 RPM, and the speed of the motor is controlled using indirect vector control. So we say calculate the reference DQ current, discharge current at the half the rated speed and half the rated torque. So here the half the speed is calculated, that is your 1455 divided by 2, 727 RPM, and torque rate half is rated torque 49.2 divided by 2, so it's a 24.8. So slip at 24.85, it becomes typically your 22.5 RPM, and synchronous speed becomes NR plus slip speed, this comes 750 RPM, and the slip stator frequency FR into NS into P upon 1, it becomes 25 Hz. And since the speed is below base speed, the flux will be kept constant. Then ID equal to ID rated, that is 8.92 ampere, and torque expression T equal to 3 by 2 V by 2 Lm square divided by Lm plus LR, that is into ID into IQ. So putting the value in the half the torque, we get IQ equal to 8.61 ampere. Coming to example 3, a 3-phase star connected 60 Hz 4-pole induction motor has the equivalent circuit parameter as RS equal to RR dash equal to 0.024 ohm, and X is equal to XLR equal to 0.12, and the rated slip of induction motor is 0.04. Calculate the motor speed and rated torque at F equal to 30 Hz, motor control with the constant V by A. So per unit frequency here it is A equal to F upon F. So rated torque is T upon 3 omega S. We rated R2 dash upon AS divided by in bracket RS upon A plus R dash upon AS square plus X plus XR square. So for F equal to 60, A 60 by 60, that is 1, and S equal to 0.04. So T equal to, putting a value, it comes like your 3 rated square by omega S, and for frequency 30 Hz, a 30 is your 30.6.5. So putting a value T omega S equal to V rated 0.24 divided by 0.5 S divided by 0.24, 0.5 and 0.04 divided by 0.5 S square plus 0.24 square. And subtracting that, we get the slip S equal to 0.084 or 0.843. So slip on stable part of the torque speed characteristic is 0.89. Now the synchronous speed for 30 Hz is 900 RPM. Therefore the motor speed is 900 minus into 1 minus 0.089, that is 820 RPM. Now coming to example 4, a 400 Hz 50 Hz 6-pole 960 RPM star connector motor has the following parameters per phase. So stator RS equal to 0.024, RR dash equal to 0.20 ohm, and X equal to XR dash equal to 1.5 ohm, XM 30 ohm. The motor is controlled by variable frequency control at constant flux at the rotor. To calculate the motor speed and the stator current at half the rated torque and 25 Hz. The solve for part 1, assuming the speed torque curve to straight line for S less than S max. Calculate the frequency, stator current, and the voltage at the rated braking torque at 800 RPM. So coming to solution, synchronous speed here it is given and equal to 120 F by P, that's 1000 RPM, and omega am rated, that is 2 pi 1000 by 60, that is 104.7 radian per second, and slip is 1000 minus 60 by 1000, that is 0.04, and rotor impedance ZR dash equal to RR dash upon S plus the XR dash, so it's come to 5.22 at the angle of 16.7 ohm. And now stator impedance Z is equal to 0.4.015, that become 1.55 at the angle of 75 degree ohm, and machine impedance Z in total ZS into plus ZR into ZM upon ZR upon ZM, it comes 6.6 at the angle of 37 degree. So IS equal to 400 by root 3 divided by 6, so it becomes 38.5 ampere, and RR dash equal to ZM upon ZM plus ZR dash into IS, so it becomes 36.22, and E equal to IR dash into ZR, that is 189 volt, and rated torque 3 by 2 omega sum RR dash square RR dash divided by S, it comes your 188 Newton meter. So first at rated 25 Hz equal to 25, 50.5. So from the torque equation, we get the, for a given torque 188 by 2, we get the slip equal to 0.0374. So omega m equal to A, omega m 1 minus S. So we get the N equal to A and S 1 minus S. Putting a value, we get 181.3 RPM. And at 25 hertz, E equal to 0.5 into 189, 94.5 volt, and Z equal to RS upon S, JXLR. So it comes by 5.4 at that angle 8 degree, and taking equal to as a reference factor. So IR dash equal to ER upon ZR dash, it comes 17.5 ampere at the minus 8 degree angle ampere, and IM equal to E upon JXM, that comes 6.30 at the angle 90 degree ampere, and IS equal to IR plus IF. So hence IS becomes 19.85 ampere. And to the slip speed in RPM at the rated torque and frequency, NS equal to NSN, and that is 0.04 into 1000 for RPM. Since the speed torque is straight line, so slip at the half rated torque is NS 0.5 into 40, 20 ampere, and 25 hertz, N equal to 25 upon 50 into 1000, that's a 500 RPM. The slip remains constant for a given torque, and motor speed equal to N equal to NS minus NS1, that is 480 RPM. And the for constant flux, the AY ratio must be constant. So at 25 hertz, E into equal to 0.5189, that 94.5 volt, and S equal to NS 1 upon NS, that comes 0.04, and ZR dash RR dash upon S plus AX, that becomes 5.06 at the angle 8.5 degree ohm. So taking E as a reference factor, IR dash equal to E upon ZR dash, and putting value, it comes 18.7 at the angle minus 8.5 degree ampere. IM equal to E upon JX, that's 95.15, that becomes 6.3 at the angle 90 degree ampere, and S equal to IR dash plus IM, putting value, it comes 20.6 ampere. And 3 at the breaking torque, the slip speed will be negative. And the slip speed at the return mounting has the slip speed is your NS1 is minus 40 RPM, and sequence speed NS plus N, so that becomes 760 RPM, 800 minus 40, and frequency 760 divided by 50, that 38 hertz, and A equal to 38 by 0.76. So 38 is equal to, with the constant flux, it becomes 143.64 volt, as equal to minus 40 by 760, it becomes 0.0526, and ZHRR upon S plus JXR, it becomes 3.97 at the angle 163.3 degree, and taking E as a reference, IR is equal to E upon ZRS, putting a value from 36.2 at the angle minus 163.3 degree ampere. IM equal to JX, that comes 6.3 at the angle minus 90 degree ampere, and IS equal to IR plus IM, that becomes IS equal to 38.52 at the angle minus 184.54 at ampere, and V equal to E plus ZIS, so it becomes V equal to 156 at the angle minus 17.3 degree volt. Now coming to example 5, a 460 volt, 60 hertz, 4 pole, 1720 RPM, star connected neck motor has the following parameters per phase referred to stator: RS equal to 0.5, RR equal to 0.2, XL equal to 1.5, XM equal to 30. The motor is controlled by variable frequency control with at a constant flux of rated value. Assume the torque curve straight line for S equal to less than S max. Calculate the frequency at 1200 RPM and rated torque. The motor speed for frequency of 30 hertz and rated torque, and the frequency and stator current at half the rated torque at 1500 RPM. So omega m rated 2 pi into 18 upon 60, so it comes 188.495 radian per second, and slip 1800 minus 70 25 18, so that comes 1800, that's 0.044, and rotor impedance ZR dash equal to RR dash upon JXR, that becomes 4.5 plus J1, and stator impedance Z is equal to 0.5 plus J1 ohm, and total impedance Z in ZS plus ZR Zm divided by ZS plus Zr, so it becomes, putting a value 5.291 at the angle at 29 degree ohms, and I is equal to 460 by 3 divided by this 5.29, so 50.19 ampere. RR dash ZF upon ZM plus ZIS, so it becomes like your 48.06 ampere, and E equal to IR upon Z to ZR, that's 22.5699 volt, and rated torque 3 upon omega, putting a value, it comes 174.90 Newton meter. And A to develop the torque rated, and R equal to N equal to 1200 pounds. So since the speed torque is a straight line, so slip speed constant for rated torque, and S1 equal to 80 RPM, and R equal to 1200, so NS equal to 1200 plus 80, that's 1280 RPM, and frequency for 1280 RPM equals speed is 42.67 hertz, and A equal to 42.67 divided with 60.6 0.711, so S equal to 81 12 80, that is 0.0625. To develop T equal to rated, F equal to at F equal to 30 rpm, slip constant for a given rated torque is 80 rpm. So NS 30 900, so synchronous speed is NS 30 minus NS1, that's 820 rpm. And to develop the torque equal to 0.5 rated torque and N equal to 1500. So since the torque speed curve is straight line, the slip speed at half the rated torque is 40 rpm. So NR equal to 1500 and S equal to 15 plus 40, that is 1540 rpm. And we can see at the 1540 rpm is 51.33 hertz. A equal to 15.33 divided by 60, it becomes 0.855. And slip is 40 upon 15, that 100, so that is 0.0266. And for a constant flux, the A by F must be constant, so hence the at 51 point E become 0.85 into 221 point, so it become 189.4338 volt. And ZR is equal to R dash upon S plus JXL, so it becomes 7.589 at the angle 6.46 degree. And taking A as a reference, so IR dash equal to E upon ZR dash, so putting value to 24.931 at the angle minus 6.46 degree. And IM equal to E upon JAXM, putting value to become 7.34 at the angle minus 90 degree ampere. And IS equal to IR dash plus IM, so hence IS equal to, putting a value, it becomes 26.76 at the angle minus 22 ampere. Coming to example 6, the 3-phase 7.5 kilowatt for 15 line voltage, 50 hertz star connected for fully square gauge induction motor has the following parameter: RS equal to 1, RR equal to 0.77 ohm, XL is equal to XLR 1.5 ohm, XM 35 ohm, J equal to 0.1384 kg meter square. Is full load power factor 0.85, efficiency 0.8. Full load speed is 1450 55 rpm. The speed of the motor is controlled using a direct vector control. You can throw pendulum voltage source converter if rotor speed is required to raise 1.25 times the rated speed at half the rated torque. Calculate the reference PQ component of stator and frequency. Now coming to solution, the rated torque is T rated P rated upon omega rated. So putting value comes 49.22 Newton meter. And now N is equal to 1.25 times N rated. So this comes 18.75 rpm, and T equal to half the rated. So that comes 24.61 Newton meter. And T starting twice the rated, it become 98.44 Newton meter. For the half the rated torque, slip speed is NS equal to 45 by 2, that's 22.5 rpm. And synchronous speed is NS equal to NR plus SNH, so it becomes 1841.25 rpm. So where NS equal to 125, so F becomes 61.375 hertz and A equal to 1.2275. Then IMR equal to IM rated upon A, so putting value it comes minus J 1.4782, and ID is the peak value of this side, so ID rated is root 2 IM, that becomes 2.0905 ampere. And torque expression T equal to 3 by 2 P by 2 LM square divided by LM plus LL into IDIQ. So putting the value, IQ comes 36.7378 ampere. Now coming to example 7, a 3-phase star connected 220 volt line to line 0.75 kilowatt 50 hertz 2 pole square cage neck motor has the following parameters value in ohms per phase, that is RS equal to 12494, RR equal to 1.412, and XL is equal to 3.502, and XLR 3.209, XM 8.25, and full load slip 0.75, and full load power factor 0.8, and efficiency 0.75. The speed of the motor is controlled using a direct torque control scheme based on pendulum VSI. The motor is controlled with the constant flux below base speed and constant rated voltage above base speed. So calculate reference torque and reference flux at the half the rated speed with 50% of the rated torque. So for the solution, 2-pole motor, N is equal to 3000, so the rated speed is, rated slip is 0.075, and rated speed is now 1 minus S into synchronous speed, that is 2775 rpm, and omega rated 2 pi into 200 divided by 60, so it comes to 90.59597 rated per second. T rated P rated upon omega rated, it comes 2.581 Newton meter. From the equivalent circuit of induction motor at slip equal to 0.75. So calculating total impedance, we get 20.61 at the angle 30.03 ohm, and rated stator current is rated VL upon Z into root 3, so that we become 6.162 minus at the angle minus 30.03 degree ampere. converting three-phase quantity to two-phase quantity instead. From the above relation, VD equal to 179.62 omega t and VQ equal to 179.62 cos omega t. And now similarly, IQ equal to 6.163 into root 2 sin omega t minus 20, IQ equal to 6.13 root 2 sin cos omega t 120. So and VD equal to IQ R plus D lambda upon dt, IQ equal to IQ R d lambda upon dq lambda upon dt. So lambda d equal to 179.62 divided by omega cos omega t minus 11.727 omega cos omega t plus minus 30. So lambda q equal to 179.62 omega sin omega t and plus 1.27 omega into sin omega t minus 30 at critical condition. The lambda d and lambda d is your minus 0.57 cos 314.15 t minus 0.0358 cos 314.15 t minus 30 degree, and lambda q similarly 0.7571 sin 314.15 t plus 0.0358 sin in bracket 314.15 t minus 30 degree, and at t equal to 0, t equal to 3 by 2 p by 2 lambda d iq minus lambda q id, and for putting a value of typically this will come 2.63 Newton meter. For half the synchronous speed, the flux remains at rated, the torque at half the rated value, iq becomes half, so t equal to 3 by 2 p by 2 lambda d iq minus lambda q id. So putting this value, t comes your 1.31 Newton meter. Now coming to example 8, a variable frequency drive consists of 3-phase 22 kilowatt for 1550 Hz star connected 4-pole square cage motor has the following parameter: Rs equal to 0.18, Rr equal to 0.12 ohm, XLS equal to XLR 0.5 ohm, XM is 12 ohm, J equal to 0.184 kg meter square. Full load speed is 1470 rpm, and full load perfect 0.86 and efficiency 0.92. It is platform long BSI with almost sinusoidal voltage source. So calculate the starting frequency and voltage across the stator winding to develop twice the rated torque and constant rated flux with the minimum current, and with the perfect to neglect the core and friction damage losses. Coming to solution, S equal to 1500 minus 470 divided by 1500, so it's equal to 0.02, and the slip at twice the rated torque twice into typically 30, that's 60 rpm, and synchronous speed typically NR plus synchronous speed becomes 60 rpm, and synchronous frequency 14 to 60 by 2 Hz, and ratio of operating frequency to rated 150 0.04. And now coming to expression of IS expression, current Vp is equal to divided by Rs plus Jxl plus in bracket I xm inverse plus Rr plus Ix upon 1 inverse of that power minus 1, and from this putting a value Is we get 42.56 at the angle minus 33.86 degree at ampere, and magnetizing branch Im equal to Is into Rr upon S plus S XLR IR plus XLR Im. So putting value, it comes Im equal to 18.46 at the angle minus 93.45 degree, and typically magnetizing branch voltage at the 2 Hz, so Im into Im. So putting a value, it comes like 8. Your Im current 8.87 at the angle minus 3.45 ampere. So rotor current is IR E1 upon RR plus I into XXM, so it comes 72.91 at the angle minus 12.91 ampere, and history current IS plus IR, to get IS 78.11 at the angle minus 26.41 ampere, and history voltage V equal to E1 plus IS into RS plus JIX. So from this putting value, we get V equal to 22.78 at the angle minus 13.68 degree, and history line voltage VS LL equal to root 3 into 22.78, that becomes 39.46 at the angle minus 13.68 volt. Perfect is cos inverse your minus 13.86 plus 2 26.41, that becomes 0.9755. Now coming to example 9, a variable frequency drive consists of 3-phase 20 kilowatt 50 Hz star connected 4-pole induction motor has the following parameter: Rs equal to 0.18, Ra equal to 0.12, XL is equal to XLR 0.5 ohm, XM 12 ohm, J equal to 0.184 kg meter is full load speed, 1470 and is full load perfect is 0.86 and efficiency 0.92. It is platform feed long ASI with almost constant voltage. Calculate the voltage and frequency of the inverter output to drive the load at 150 rpm at 150 Newton meter, and the motor perfect, and neglect cold loss and frequency. So coming to T rated, P rated upon this, so it comes 142.91, and slip at 150 RPM comes like your slip speed at 150, it comes 31.46 RPM, and synchronous speed is NR plus synchronous speed becomes 181.46, and stutter frequency corresponding to this it comes 6.048 Hertz, and slip comes NS upon NR, it comes 0.1733, and A equal to 6.04 divided by 50, that's 0.12. So E1 is IM into A into IXM. So putting the value, E1 comes 26.82 at the angle minus 3.45 volt, and the IR is typically E1 upon RR upon S plus JXR. So putting value, IR comes 38.6 at the angle minus 8.40 ampere, and the hysteresis current ISRR plus IM, so it becomes like a putting value 44.21 at the angle minus 33.101 ampere, and hysteresis voltage B equal to E plus E1 plus I Z into in bracket IRS plus ALX. So the voltage comes now putting a value 30 V equal to 35.00088 at the angle of minus 6.09, and the line voltage is 330 this value, so it comes 60.77 volt, and power factor cos inverse minus 6.05 plus 33, it becomes 0.81891. Now coming to example 10, a 4-pole induction motor has the following parameter: P rated 80 kilowatt, T rated 140 Newton. Use the following parameters for machine: R1 12 milliohm, L1 50 microhenry, Lm equal to 2 millihenry, L2 40 microfarad, and R2 4.8 milliohm, and T and L equal to 2 Newton meter. Calculate the input per phase current, voltage, frequency, power factor, and machine efficiency when operating at full load and twice the rated torque. Assume the slip of 1.5%. So rated rotary speed is omega rated, P out upon T rated, so that comes 1142.9 radian per second. The frequency at which the rotor is rotating, FR equal to omega R upon 2 pi, that comes like your 181.89 hertz, and the synchronous frequency F synchronous is R rated upon 1 minus S, so it comes to 184.66 hertz. The slip frequency F slip equal to F synchronous R, putting a value, it comes like your 2.77 hertz. So now the electrical frequency F equal to P by 2 F synchronous, so it comes like 369.32 hertz, and the no load or core, the friction voltage loss is P CFW equal to TNL into omega R, it comes 2.286 kilowatt, and when operating in the motoring mode, the electromagnetic torque and the power are the sum of the output and the no load losses. So T induced equal to T load plus TNL, it comes like a putting a value 72 Newton meter, and P converted comes the value, typically putting a value, it comes 82.286 kilowatt. And for a given slip I2 dash equal to T induced upon omega slip ITR2, it comes 295 at the angle 0, and the rotor reflected rotor impedance ZR equal to RR dash upon S plus J omega EL dash, and it comes 0.32 plus J 0.0928 ohm, and the back EMF is equal to I2 dash ZR dash, so putting a value, it comes 98.29 at the angle of 16 plus 16.17 degree volt, and the magnetizing current is given IM equal to EM upon omega EMF, so it comes 21.18 at the angle minus 73.82 volt, and the per phase current is the sum of the reflected rotor current and magnetism. So I1 equal to I2 dash plus IM, putting value comes 301.59 at the angle minus 3.87 degree ampere. The hysteresis impedance ZS equal to ZR R1 plus J omega XL. So the voltage drop across the hysteresis impedance VZCH I1 ZS, putting a value, it comes like a typically 5.97 plus J 34.66 volt, and the per phase supply voltage is P phase plus ZPS. So putting the value, it comes 118 at the angle of plus 31.72 volt. The machine power loss is the sum of the unique core and friction voltage and losses. PM loss equal to P CFW 3I1 square R1 3R1 into I1 square into 3R2 I2 square. Putting a value, it comes like 68114 watt. And the machine input now P in equal to P out plus P losses, so it comes 86.814 watt, and efficiency is your P out upon P in, so it comes like 92.15%, and the machine power factor is P in upon 3 VHI, so it comes 0.8131. And coming to now your power quality improvement in induction motor drive as a case study. So first is the improved power quality converter at adjustable speed induction motor drive. So power quality problems in induction motor drive are the uncontrolled AC/DC converter, an energy storage element like a capacitor filter, so they cause large harmonics on the AC current, and of course the VSI, injection of harmonics into AC main, and the voltage distortion due to the voltage drop caused by harmonic current flowing through the system impedance, and poor pipe reactor, equipment overheating due to the harmonic current interruption, and variation in DC link voltage with fluctuations in voltage of input AC supply, and malfunction of sensitive electronics equipment, and interference on telephone and communication line, and decreased rectifier efficiency. And this typically block diagram how really typically variable consider I use the 3-phase uncontrolled rectifier with the capacitive filter and then 3-phase inverter, of course with the speed feedback as well as 2 currents, with of course proper control in the processor, may be controlled by the typically from the PC command. So input current is your quite distorted, you can say it's not sinusoidal, and it has to be, of course we can use the improved power quality converter like with the in place of diode with the maybe IGBT, and we should get a sinusoidal current in phase with the supply voltage. So this is to be modified in that way. So you can see, I mean, when AC machine current waveform, AC mains current waveform and harmonic direct or control motor with a simple diode is rectifier and rated load condition. So rated load condition, you can see how the peak is 60% TAD, and at light load is a PAD of typically around TAD of 104.93% at 20% load. However, there is a power quality system like IC 61032 limits for different harmonic for all power, all low power single phase equipment, and IEEE 519 limits on voltage and current distortion. So this is IEEE 519 standard. The current distortion limit for given for general distribution system for voltage range 120 to 69 kV, and maximum current harmonic current distortion percentage of load and IL individual harmonic current, and you can clearly see the all the typically for short circuit level, that's a short circuit impedance depends on all circuit the what are the harmonics permitted of 10 total demand distortion factor 5% when short circuit impedance is quite high, and then 8% if short circuit impedance is low, and then 12% and 20% when you have it even the typically more than 100. That's all, I mean, like short circuit level, like, so that is a typically 0.01% short impedance, so TAD of the voltage will not go more than 2%. Now solution to power quality problem AC mains is passive wave shaping technique like passive filters, various combination of passive series, shunt and hybrid, and multi-pulse converter. Increase in pulse count reduces the harmonics and makes the waveform near sinusoidal. Therefore, various combination of isolated, non-isolated multi-pulse transformer like 12 pulse, 18 pulse, 24 pulse, 36 can be used for improved power quality. And then active wave shaping technique, typically that improve power quality converter for single phase or 3-phase and unidirectional or bidirectional. Now coming to adjustable speed induction motor drive for this power quality improvement. I mean, so this is typically the with the filter control that the normally we use in a laboratory environment with the loading of DC motor, and next motor is controlled with the typically with the vector control, which is really simulated in case of processor like DSpace, and then you have a rectifier inverter efficiency typically, and this is for case of a system component different control with the director control. Then freedom to control the block diagram, how we control it, we already explained the reference. We have a actual speed and then the flux calculation depending upon the rotor speed, we get the IDS and then IQS from torque speed controller, torque pushing, and from which we get slip speed, we get the from solid speed we get a stator frequency and then flux angle to convert from your IDIQ into alpha beta, and from this I alpha beta we can convert 3-phase currents, and we have a 3-phase control with the feedback current. And this is typically the DTC, how we really have a functions to winding current and DC voltage and speed, we calculate torque and flux, and from torque speed we get a from a reference speed the reference flux, and the from speed control reference torque, and then we have a torque control, both 2-level flux control and 3-level flux control with the hysteresis errors to go to table of optimal switching or voltage switching table, which gives the switching signal for the typically for the inverter. But of course these signals are given for torque and flux estimate also in detail. Is the typical, you can call it experimental setup for the hardware for implementing these both filter control and director control. And these are the typical interfacing circuit for the current sensing signal conditioning circuit and the photograph of current sensor, and these interfacing of voltage signal and the PCB or current typically voltage signal, and these optical isolation for from the DSP signal to going to be typically for the inverter. for high voltage side and photograph of it. And this is a simulated waveform starting and sudden change in reference speed, how the supply current and how the winding currents are there for starting, as well as your typically reference speed increase change of the load also. And this is the case with the dynamics of this your field under control during the field beginning. But you can see how the typically your supply current are there, and it has TAD 60%, 100% load, and 20% 106% TAD. And then typically the your supply power quality issues with your motor side as typically AC means voltage harmonic distortion at 120% load. The voltage distortion also caused because of high harmonic current. The voltage distortion is 6.71% TAD, and at full load at 20% load, because you draw less harmonic current, so it becomes 2.72. The voltage is also distorted point of common coupling, and this is the variation of TAD versus of AC means current power factor variation, the load torque of this diode bridge rectifier. And these are the typical values, like you can say, of different loads from 100% to 20% for supply current typically value, as well as the TAD and the crush factor, distortion and displacement factor, and power factor, and as well as the DC impedance. These are experimental results, how you can see the supply current and with the voltage, how the voltage are distorted, and how the three phase currents are there in the next one, mains current, and how the motor voltage and motor currents are there. Then during the dynamics of vector control, like typically starting experimental results and then field weakening. This typically corresponds again for change of reference speed and then the field weakening, and then your for sudden change in reference speed, and typically the different variable three phase current, supply current, and then your sudden change in load torque, and then the power quality issues. The TAD of the supply current becomes like on current is 40% TAD, and current TAD is 40%. Voltage also get distorted with that 6.8% TAD because this harmonic. You can say what is the kind of voltage waveform. So you can see on about recorded waveform, and this is corresponding to like typically at your with the light load condition. So here TAD goes like a 62.8% experimental one, and voltage distortion is 4%. And this is of course the TAD with the load torque and as well as power factor deterioration. And these are the typically of course the various power quality diode bridge rectifiers, and this is the typically power quality performance stator ML of the motor, like TAD of current 3.1%, and light load condition it is around 6%. And these are typically starting and sudden change in reference speed, typically in direct torque control. So you can of course and how the supply current distorted and supply voltage are distorted, and then this is during the sudden change in the load torque, field weakening and load change, and the TAD of supply current typically of 60% TAD and 104% TAD, and the typically supply voltage distortion and the power factor variation and the performance, and experimental result correspond to supply current and the dynamics. And then of course during the dynamics operations of voltage and current and performance and power quality issues, and the supply voltage, the supply current TAD about 39.46% and voltage TAD 6.7%, 100%, and under 20% load TAD of supply current 64.3 and TAD of voltage 33%, and then the TAD of typically of you can call it of TAD of AC mount current and power factor, and the data corresponding to that, and then the distortion 37.8% TAD of the motor stator ML, and the TAD of the current is quite at light load at 20%, 15.1%. So coming to the conclusion, the use of diode bridge rectifier at AC mains of drive causes variation in DC bus voltage as well as load torque and AC mains, and diode bridge rectifier cause poor power factor and high current harmonics in the AC mains. The power quality performance deteriorate the load torque, and this emphasizes the need for improved power quality converter instead of diode bridge to mitigate the power quality problems at AC mains. Now coming to classification of configuration of your improved power quality converter fed adjustable speed drive. So now for classification of improved power quality converter, if we talk about, you can have a unidirectional like maybe boost type, maybe third harmonic modulator improved two switch and Scott connected, and then buck type improved quality converter, then buck boost type and multi-level type like boost type, and three switch and the buck type. And for bidirectional we have a boost type 2-level voltage source converter, then buck type improve power quality converter, buck boost type improve quality, and multi-level improve quality like a 3-level or higher level. And this is a typically detailed comparison of various improved quality like a Minnesota rectifier, Scott transformer based improved quality rectifier, Wiener rectifier, 2-level rectifier, 3-level voltage source converter. Now coming to third harmonics modulated 2-switch improved power quality pad field control based induction motor type. So this is typically like also called like Minnesota rectifier. So we have a typically kind of boost converter with ripple injection. So only 2 switches are used here, and it provides the advantage of you can say harmonic reduction in supply side as well as the chilling voltage regulation with the proper motor control. And the current on the supply typically of the rectifier becomes of this shape, but supply current becomes the typically on the output current of this shape. And then with this you get the motor current also typically of this nature. So supply current becomes sinusoidal after the ripple injection, as you can see here, the voltage and supply current. And these are typically the control for your control thumb of the total controller of this of RST and this control of Minnesota rectifier with RST controller. So typically coming to control thumb, polynomial RST controller is based on the pole placement theory where the 3 control variable RST with closed loop poles are placed in desired location to get the most preferred response, and polynomial R is placed in feedback path for polynomial S and T are placed in feedback forward path. So polynomial R and S are responsible for reducing the steady state error. T tracking is responsible for desired tangent response. So now these are robustness of RST controller. You can see what are the blocks in this and overall closed loop transform of this RST controller for this purpose. And these are the body plot, of course, for frequency response as well as frequency response of sensing of noise of RST and PI controllers, and the step response of PI controller open loop now. And this is typically the control structure, direct or control with stage and flux controller. So reference speed we get the reference flux, and from this we get the ID, and then from this we get the speed control, we get the reference torque and initial frequency. Then we calculate of mass transformation alpha beta and then inverse clock LEB, and then current control with the feedback of current stereo current. This is the experimental setup. These are the typically the current reference. You can call it reference current with the RST controller, and these are typically you can call it simulated performance of steady supply current, supply voltage, and speed. And then you can see how the typically the diode rectifier current, how the injected current, and green is the supply AC mains current get improved. And this is the case of course the performance of this sudden change of the reference speed, and how the supply current is there second waveform remains sinusoidal during different dynamics like starting also. During starting with well frequency diode, it does not draw much larger current or power, like it draw only the very small power like performance. And this is the case when you have a sudden change in the load torque, how the supply current also changes. And these are typically power quality like a TAD reduced at 100% 3.78 and partial load 20% 6.92%. TAD current remain closer to sinusoidal, and then corresponding to 100% load mains current with the PI controller 4.8 and 10. So with the RST controller it's reduced, and then this is with the RST control again for AC mains voltage TAD like for 2.17 and 2%. And this is how the typically you can call it with the RST controller, the TAD reduces and the power factor improve. And these are the performance of course with the you can get RST controller that you get the power factor 0.99 in all cases. And this is the supply, you can call it inductor current in that case, and the inductor current typically shown in case of the circuit. And then you can say the performance of the steady state supply voltage, supply current, DC link voltage is well regulated, and typically the capacitor voltage for all 3 phase currents. And then the AC mains current and direct wire input, and the typically the analysis of diode current, injector current, and finally supply current in upper mode with PFC operation. The starting, like how the supply current still remains the sinusoidal during even starting also, and during dynamic speed change and field weakening. Then typically sudden change in reference speed, and then typically the supply current during the 100% load, and during dynamics during sudden change in the load torque, how the supply current changes as well as motor current changes. And the TAD of supply current 4.1% and supply voltage is 0.4%, so it is reduced less than 5%. with this converter. Under light load it is 11%, the voltage is 2%, and how the typical TAD and power factor improve with this, typically with this control, and these are overall performance of this control. Now coming to another concept of power quality improvement is this variable index motor valve frequency drive, like it's got transformer based 2-switch improve power quality fed field under control of index motor drive. So this is a typically Scott connected transformer with 2 PFC, 2 power factor correction boost converter, maintaining the 2 equal voltage for 3 level inverter feeding index motor drive, and with the power control of the 2 PFC. If they are maintain equal power, then 3-phase supply current are balanced at unity power factor. So this is the control how we are controlling the 2 ditch, typically the 2 PFC with the incomplete DC link voltage, and typically inductor current of boost converter for the 2 boost converter. And this is the motor control how we go ahead your field index control with the motor control for 3 level control. Here also we get 12 pulse PSI, and this is the experimental setup for the system, and this is the typically the DC link voltage how it is varied on dynamics of Scott connect one. This is the simulated performance, like you can see how the your inductor current, how the typically the capacitor voltage, and how the 3-phase supply currents are there, and motor voltage and motor current. And this is the dynamics performance how the supply current remains sinusoidal during starting, during reference change, and decrease in supply speed, and the supply current during the typically field beginning and sudden load change. On the top is supply current which are sinusoidal, and the TAD of supply current is 2.59%, and the 100% and light load is 4.78%, and typically your power quality, I mean in the at full load and light load, typically you are 2.52 and 2% of voltage. Voltage also a little bit, but reduction is, and TAD how really it is changing less than 5% with the load, and power factor improve, and the power factor remains above 0.9, around 0.99 up to 40% load, and the experimental result corresponds to 3-phase of mains current you can see very close to sinusoidal at full load, and different parameter, and during starting how the supply current remains sinusoidal even during changes during dynamics, and then during the DC link voltage how it is regulated even during the field weakening, and typically certain change of reference speed how the supply current is, typically the voltage and supply current is remains there, and the how the with the change of the load how the supply current is increases and decreases, so with the change of the load, and the TAD of supply current is 4.1% at full load and 1.7% for the voltage, and for the light load it is 20%, 8.4%, and voltage TAD is 1.7%, and how the this is improved with the load, TAD reduces increase in load, and power factor improve with the load, and the TAD, I mean power factor remain 0.99 in all the cases. Now coming to the conclusion, the dynamic performance of this improved field under control, the input power quality indices have been improved significantly when Scott connector based quality control feed forward control is used as compared to the conventional one. The DC voltage loop with forward control has been yielded fast response with reduced overshoot, and proposed drive system results in much less input current, AC mains current, TAD improved power factor, provide range of low torque as compared to the conventional diode rectifier, improved vector control for building a constant switching frequency operation with reduced stator current and torque level in obtain using space vector modulation. In this type, this got transform improve power control DC link voltage very much suitable for 3-level typically NPC, and the DC link bus voltage even balance problem in 3-phase inverter is overcome by maintaining it using Scott transformer at front end. Now coming to 3-switch 3-level improve power quality at DTC based induction motor drive, and in this case you call Wiener rectifier. We are using Wiener rectifier for feeding the typically the 2-level voltage source inverter with power control, and this is the control of how really we are controlling this Wiener rectifier, the switching of different 3 devices of 3-phase, and this is the motor control we already discussed it, and this is the typically the, I mean like you could photograph of the total hardware implementation, and this is the simulated waveform supply current, I mean typically how the converter voltage and the capacitor voltage both are maintained equal, and typically the your stator current and the speed, and how during dynamics like starting reference speed change and increase, and how the supply current is maintained sinusoidal, and how during field weakening and sudden change how supply current changes but remains sinusoidal, and TAD of supply current remains 2.69 at 100% load and 4.51 at 20% load, and the voltage THD typically 1.73 and with a light load 1.57, and how the THD of current reduces less than 5% with the load, and with the power factor improve the load. And here the all power factor remains 0.955 and THD remains less than 5%. And these are the typically experimental results under steady state of the Wiener rectifier, how three-phase currents are balanced and channel mains current, and how the typically the mains current increases during the speed change or during starting, and how during the speed change, and typically the your mains current during the load change, reference speed change, and during the load change, how the supply current changes in motor. And here the supply THD current is 4.7% and 100% load with a voltage THD 2.7% and light load 12.9 and 3.1%, and load how with the load THD of supply current and power factor improve. And here also the power factor remain 0.99 for all the load variation. Now coming to two-level pendulum voltage source converter fed direct or control index motor drive. So here we are doing three-phase voltage source converter on supply side as well as on motor side with the power control. The DC link voltage is maintained as well as the power current is maintained on typically on supply side. This can have even the regeneration. So this is the control how we really control the DC link voltage with the two supply current, and we calculate the active and reactive power, and reference reactive power is 0. So that gives EQS, and from the typically from DC link voltage control as well as the active power required, we add together and we get the typically the required power by the motor. So all we three add, so it gives the VDS for the converter. We convert this VDVQS with the typically from the angle, we convert to V alpha beta, and from this from V alpha beta we generate the using space factor modulation, we give the switching for voltage source converter of grid side. And these are phasor diagrams how really it's operated for typically of voltage source converter of the grid side. And this is the motor side control we already discussed for stage is typically of direct torque control. We have a reference speed, we have estimated speed. So we have a speed control, we give a reference torque, and from this torque we get the typically slippage speed, and from reference from actual speed we get the flux, and here we get the angle. So we are able to transform the flux into dq, and we have estimated flux, so we are able to get dq flux, and from which we get the typically the taking a feedback of current, we get the reference voltage which we give to space factor modulation. So coming to typically the control, here we use the gain schedule PI controller. The proportional integral gains are varied with respect to the input error, and the speed loop gain is expressed as a function. So we get the gain modification kpw kp max minus this. So kp w minus kp minimum e to power k r into it, and from this speed loop integral I do express as a function of ki equal to 1 minus rho ki max. Rho decide the variation of ki from 0 to ki min is given, and rho is tan inverse kn. So and eta is a constant which decide the rate at which the rho is changed from 0 to 1, and eta is given by eta equal to eta error minus eta, and then eta equal to ck to omega r dash, and ck is constant. And this is how the control thumb for the typically the motor control comes here with the speed loop, and how the design of body plot of this gain schedule PI controller, and the performance like the supply current and the converter voltage, pendulum voltage, and then the motor voltage and motor current and speed, and how the supply current during starting and typically the reference speed change, and how typically you can say during the decrease in speed, how the supply current is there and motor current, and the high supply current during regenerative braking, because this can have a regenerative braking also. So you can say that clearly the reversal from three-phase stator current, I mean where the frequency changes and the speed changes from 11 rpm to minus 11 rpm, and supply current THD under steady state is 2.11%, and the light load condition 4.78%, and the voltage THD is 2.36, and light load voltage THD 0.54, and the converter voltage pendulum voltage THD is 51%. So you can say small. Typically the filter makes the THD quite low, and the THD of less than 5%, and power factor on supply side, and your power factor remains 0.99 in all cases. And these are the actual, you can call it experimental results of typically of three-phase supply current and motor current and DC link voltage, and for 100% load, and supply current remain in phase. As you can see here, DC link voltage regulated, and this is during starting, the AC mains current and DC link voltage, and during typically your with again schedule controller, and then during the speed reversal, because it can have a speed reversal, how the mains current direction is reversed during regeneration, and typically the torque controller. So these are the performance during the dynamics like speed reversal, because this can have a regenerative braking at clearly CU, and then the field weakening, and typically the regenerative braking clearly you can see for short period there is a regeneration current direction reverse of AC mains current, and DC link voltage remain constant. Then the sudden change in reference speed, the response of your mains voltage and mains current, and DC bus dynamics also here for the sudden change of load from your 50% to 100%, 100% to 50%, and farm load change from 20% to, and DC link voltage regulation. And here the TAD of supply current remains 2.8%, and voltage TAD 3%, and for light load 4.8% with TAD of voltage 3%. And this is the really harmonic spectrum of converter line voltage, which have a quite large TAD, and typically your current TAD is still quite low, 2.95%, voltage TAD is 18.6%, and power factor, total harmonic resistance power factor of supply current, and power factor remains above 0.99 in all cases. And here in the 100% load, the TAD of supply current 3%, and 20% 6.3%. And these are of course the parameters of this under dynamics. Like now coming to 3-level period-long voltage source converter pad direct torque control. So this is here on grid side also we use the 3-level converter for improved power quality and improving the power factor, as well as we can have a regeneration also, and motor side also we have 3-level. These are used for high level. So we have control of course of this front end 3-level control as well as motor 3-level control. The advantage is we can reduce the switching frequency as we go on increasing the number of levels, and the high increasing levels, so we can reduce the rating of voltage and current rating of the device. So this is the control of again of the converter. So we sense the DC link voltage, supply currents, so we calculate the power, so we calculate the DC link voltage as a loss, then the power from supply, so we have a reference power of loss component as well as the power drawn by motor, that becomes reference power. We have estimated power, we put PI control, get VDS, and reactive power V0, we have estimated reactive power, so we get VQS, and from transformation we got from DQ to V alpha beta, and then from DC link voltage we calculate converter voltage compensation, and we get the V alpha beta for 3-level voltage source converter on the grid side, and give the gating signal for all the 12 switches. These are typically the motor side control for again 3-level voltage switch from typically the direct torque control, typically for 3-phase inverter. And this is how we are really able to estimate the speed from the model reference technique by sensing voltage and current of the motor, estimating, and then estimating the speed from this. I mean, these are the equation for estimation of flux from voltage and current, and these are the estimation of the flux quantity from adaptive model, and these are typically the estimation of error from which we get the speed. This is the space factor modulation for 3-level voltage source converter. There you have a lot of combination here, you get it, and then the switching description of switching function, how really you decide to form the V alpha beta, we calculate the voltage magnitude, and as well as theta, that is tan inverse VL beta upon VL, and from which we calculate how we calculate the switching for space vector modulation for this 3-level converter. I mean for inverter and converter switching both of virtual all, and this is the typically AC mains current TAD with a different effect of inductance variation of the input side, and then typically of AC mains current, and this of course you can say supply voltage, supply current, and converter voltage, and then the motor voltage and there, and then typically during dynamics like starting and speed reference change, increase and decrease, how the supply current are there, even for short period it can have even the DC link still voltage maintained very well, and this is the case of sudden load change, and this is during the regeneration, because this 3-level converter, the voltage source converter, is capable of regeneration also, so it regenerates power to the grid for, and you can see reversal of the current and load torque also, developed torque also become negative during that, and the flux, you can see how the flux also sequence changes, I mean estimated flux like that, and the TAD of supply current it becomes 1.16%, and the supply current TAD 4.8 at 20% load, and voltage TAD of 2.2% full load, and at light load around again 2%, and typically you have a TAD of supply current at at 900, you can call it full load. Only low frequency switching 3.25 and typically on 12 band at light port and 2 volt TAD out of 1 band, and typical converter TAD 36.56% and power factor TAD of supply current and power factor improvement, and the power factor remains 0.99 in most of the cases. And the experimental result corresponding to that, you can see how the three-phase supply current and how the three-phase motor current and the supply voltage, supply current in phase, and how the capacitor voltage are maintained constant, and the converter voltage, and typically the pure stator voltage, stator current, and the supply voltage, supply current remains sinusoidal in both, and motor voltage also remains sinusoidal. And then how the mains current during starting and motor current, and the mains current during typically of your driving for the purpose of starting, then the typically of your reversal, speed reversal, how the mains currents are there, as well as during your field picking also, and during regeneration also how the supply current is there, and then the sudden change in reference speed, then change in reference speed further, and then your mains current typically at 100%, load change from 50% to 100%, then your typically at sudden change in the load torque at, and then your sudden change in load torque, how it is reflected on mains current, and typically at full load how the TAD 1.5% of supply current and 2.6% of voltage TAD on supply, and 20% how the volt current TAD 4.7 and 2.5%, and then typically at your at 9 hertz with the effect of 6 millihenry, and the current TAD for this 2.13% and at 20%, and how the voltage waveform TAD as well as here the converter voltage, and the TAD of supply current and TAD power factor improve, TAD reduce, and the power factor in all cases remains at different loads also 0.99%, and the supply current TAD 2.1%, and light also TAD of supply current remain 2.5%. And thank you.